Okay, so this problem is a little tricky. You need to find the minimum force required to keep the block at rest. So that means, velocity of zero. So when the sum of the forces are zero. So let's draw a system, and you can just call this block, it doesn't matter. And we're going to think about all of the forces, all the different interactions between the block, this guy, and any other systems. Let's go ahead and call this block M too. That's going to help us. So the first interaction that I'm going to see is this force that is straight down on the object. Now I'm going to make this very, 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 very big. This is a big dot. And I'm going to draw that applied force down here and call that F. So that's some external force. Could be your grandmother, your cat sitting on there. One of them's got a big butt. And you need to think about how much force is going to be pushing this block into the surface. So the next interaction that I see is at this surface here. There are going to be two surface interactions. One is going to be some resistive force, friction, and then some supportive force that's normal to the surface. We're going to call the normal force. So the normal force, I'm actually going to draw this on the picture. The normal force would be perpendicular to the surface. So it would look like that. So our normal force is actually going to go up, and this is going to be quite a big normal force because it has to be bigger than this external force that's pushing into the ramp. So that's our normal force. And the frictional force, well, in this case, it's not actually going to be down because what we're asked is what is the minimum force necessary to keep the block at rest. That would imply that a lot of the weight is pushing this object down, and we would expect to see some frictional force going up. So that would be, imagine the force not being put on the block. This block would slide down the ramp, and then if the motion was down the ramp, friction would resist up the ramp. So this is going to be our frictional force up. Okay, now we've saved the trickiest force for last, and that's the weight force. You can see that all of these forces are either parallel or perpendicular to each other, but the weight force is straight down. So the weight force is straight down, and we'll call it mg. And here's where we need to be careful. We need to resolve this weight force in such a way that it creates two components that are parallel to the normal force and the applied force. I'm sorry, parallel to the normal force and the applied force, and then also parallel to friction. So here's what we're going to do. We are going to turn this into a weight perpendicular component, and then a weight parallel component. You need to be careful and realize that this angle here is actually right there at the tail end of my weight vector. So now I have turned this weight component into a perpendicular part, so that's going into the ramp, and then a weight component that's parallel, so going down the ramp. I'm going to go ahead and write down here what those things are equal to. The perpendicular component is going to be the magnitude of the weight times cosine of theta because it is adjacent to or touching this angle. And the parallel component of the weight is going to be mg sine theta because it is opposite of this angle. Okay, so now we're ready to think of this problem statically so that there is equilibrium. And we can add up not the x and y forces, but the perpendicular and parallel. So let's start with the perpendicular. The perpendicular forces, and again, that is forces that are perpendicular to this surface. The forces that are perpendicular to this surface of the ramp are going to be the normal force, the applied force, and the perpendicular part of the weight. And I can see here that the normal force would be positive, kind of up, and the perpendicular component of the weight and the applied or external force, those things are going to be negative. So we'll say normal force minus applied force minus weight perpendicular equals 0. Okay, then I am going to think about all of the parallel forces, which there are two. There is friction, which let's say up the ramp is positive, doesn't really matter, and then down the ramp is negative. So this is going to be like this is right, this is left, minus then the parallel component of the weight, and this equals 0. Okay, so now let's start filling in some things here. First of all, this is asking me what the minimum force necessary to keep the block at rest is. So really what that means is find F. That's what we want to do. We want to find F. And we have terms over here. So we want to find F in these terms. and these don't look like the terms that I'm asked for, so I'm going to start plugging in equations and reworking things until maybe I see something clear. So to rearrange this for force, I would just add the force to both sides, and I would see, oh, okay, so force, the external force, is going to be equal to the normal force minus the perpendicular component. And it looks like from sorry about that. So anyway, after you put this equation together, you're going to then go down to the parallel forces and think about friction being equal to the parallel component of the weight. And I'm going to think about the parallel component of the weight as mg sine theta. Then instead of thinking about friction, I'm actually going to use the definition of friction, which is the coefficient of friction times the normal force, and set this on the left side of the equation. Now, the reason why I'm going to do this is because this will allow me to solve for the normal force in terms of mu, mg, and theta, which I see a lot of these here. So I'm going to go ahead and divide both sides by mu, and I find that the normal force is going to be mg sine theta over mu. Okay, so I'm going to take this value next that we just got for the normal force, and I'm actually going to plug it into my perpendicular equation. So I'm going to plug it in up here, and to give ourselves a little room, let's kind of bring this over here. So the external force is equal to the normal force, which now I know is mg sine theta over mu. And I am going to subtract from that the perpendicular part of the weight. And the perpendicular part of the weight is actually, if I plug this equation in, mg cosine theta. Okay, so now I have to do a little bit of algebraic stuff, and I have to sort of break this apart. So the first thing that I can do is I can pull out mg. I'm going to get mg sine theta minus, mg and then sine theta over mu minus cosine theta. Now, it's kind of hard to see this, but when you factor out 1 over mu, so again, if I factor out 1 over mu, write it like this, then sine theta over mu minus cosine theta actually becomes sine theta minus mu cosine theta. This might be hard to see, but it makes sense because if I multiplied sine theta by, so if I like factor this back in, if I multiplied sine theta by 1 over mu, then that would become sine theta over mu, and mu cosine theta times 1 over mu would just become cosine theta. So this still works, and this helps us to understand what the final answer is of the problem, which they write it like this: sine theta minus mu cosine theta whole thing over mu. So this is the final answer, that is E.